Jennifer Lago. I'm a graduate student at the University of South Florida in Tampa. I work under Dr. Matthew Pasek in collaboration with the Center for Chemical Evolution. My work revolves around geochemistry with the incorporating phosphate into your biomolecules. So let's see here. Okay. So just a brief overview of the phosphorylation problem. In prebiotic chemistry, incorporating phosphorus into your biomolecules has been a known problem that has been studied for years. It's actually a two-part problem, part of it being phosphate itself, that the predominant phosphorus-containing minerals on the Hadean Earth would have come from the apatite mineral group, the calcium phosphates, which are actually very insoluble in water. The other non-biogenic phosphorus-containing minerals would have actually been more rare and in niche environments, so I have been sticking with the apatite mineral group, but that leads into the next problem with phosphorus, which is that, as I said, it's insoluble in water, your apatite is. The phosphorylation reaction itself requires a dehydration step, which of course would be unfavorable in a water-based solution. So historically, scientists have used multiple routes in order to overcome this problem. They've incorporated condensing agents into their systems, such as urea or cyanamide. They've done high-temperature heating in order to drive off water within the system, and others have used non-aqueous solvents, such as formamide or the deep eutectic solvent of urea choline chloride. And more recently, out of the Center for Chemical Evolution, Dr. Bakar had worked with an alternative solvent called UAFW, which is urea, ammonium formate, and water. There's a lot of unique features that we discovered with this UAFW. We found that just in this system alone, formamide is actually created under mild heating conditions. It actually increases the solubility of phosphate-containing minerals and promotes phosphorylation. It has very broad temperature stability. Ammonium formate and urea itself forms a solution with a freezing point as low as -30 C and is used throughout industry as a de-icing agent. And the components of it, the urea, the ammonium formate, and the water, were all prebiotically available components. Now, as I said, Dr. Bakar and his collaborators at the Center for Chemical Evolution had published a paper in 2016 utilizing this alternative solvent in a 1:2 to 4 molar ratio. Not only was he able to phosphorylate adenosine within this system, but he also showed that by doping in some magnesium chloride, he was able to actually convert hydroxylapatite to a more soluble mineral called struvite. It is important to note that in his work, he did use a urea water system without any ammonium formate available and was actually got no detectable results of phosphorylation. So this led into my work with this alternative solvent. What I wanted to do was to determine the actual robustness of this solvent in more than just the 1:2 to 4 molar ratio, and to determine how prebiotically available would it have been geologically on the early Earth. So we started with urea formation. Now we know that urea has been detected in comets and meteorites, and that urea is actually just urea formation comes from a simple reaction between ammonia gas and carbon dioxide. So we did some thermodynamic work and just plotted the urea formation on a log-log plot of the partial pressures of carbon dioxide to ammonia, and found that even in a lower ammonia atmosphere that you would have urea formation from temperatures. The red line, let's see here, the red line at the bottom is when the temperatures are at 0 degrees. Anything above that, you're going to create urea. And then I also plotted it at 100 degrees C, and you can see that you would have urea formation up there. So we were satisfied with the fact that urea itself would probably have been available in a lot of different geological settings, just made out of the atmosphere. So we wanted to move on to the ammonium formate. Now, for the ammonium formate, we envision more of a Darwin's warm little pond theory. So this is a model system of a lake with an input of hydrogen cyanide from the atmosphere. Now, hydrogen cyanide hydrolysis end product is ammonium formate, and of course the mid product of that being formamide, which has been used throughout prebiotic chemistry. So what we did was took just a small lake, added in a daily input of hydrogen cyanide to it coming from Malakowski's, I'm not sure of the pronunciation of the name, 2002 paper in PNAS that showed that just a small amount of hydrogen cyanide over time would actually form or would fall into this lake and hydrolyze into ammonium formate. And as you can see here, in just 20 years, we can actually get a molar concentration in the lake of about 0.45 moles of ammonium formate. So we said, okay, we know water's going to be available, ammonium formate, urea. It seems like it'd be plausible in a lot of different conditions. But what happens in different molar ratios of this? Because a 1 to 2 to 4 molar ratio is very specific and might only be found in certain areas. So what I did here is I just took multiple different molar ratios of the UAFW, plotted them on a ternary diagram, and after 3 days, just took a look at the physical characteristics. And you can see from the, there we go. You can see from the top picture up here that in a lot of the molar ratios where you have urea in an excess, in 3 days the system dries out to a completely dry system. But it's at 72 degrees, open to the atmosphere to allow the volatiles to escape. And there are some molar ratios that remain liquid. So on the ternary diagram, I just plotted the green dots being what remained a liquid and the red being a solid. And you can see that there's actually quite a decent area in there in which you would remain a liquid environment within just the 3 days. Now, this is not doing any wet-dry cycling. This is just allowing it to sit open in the oven. At the same time, I wanted to see what the solubility of hydroxylapatite itself would be within this UAFW at the different molar ratios. So again, we created up 10 milliliters of each of the different molar ratios, added in some hydroxylapatite, put them in an oven at 74°C, left open to the environment to allow the escape of the volatiles, and after 14 days, we analyzed these samples on an ICP OES, and that was actually through our university and in collaboration with St. Louis University with Paul Brocker and Rio Fabrian. And the results that we got from that, we plotted again on a ternary diagram, and it was actually quite surprising. What we found was that, and you can see here that in the results, the free phosphorus, there's actually quite a bit of the molar ratios where we had 70 to 100% of free phosphorus available in this UAFW, meaning that the UAFW itself actually solubilized apatite. There's a decent amount there that is within the 30 to 70% range, which is still remarkable compared to not soluble in water. But then there's also a very specific area in which there was no free phosphorus or very little free phosphorus available in this solution. And let's see here. So on that dotted line I drew there, you can see that it actually follows the trend between where you have a high amount of free phosphorus available versus a moderate to low amount. And what we found was that the more urea that is in the solution compared to the ammonium formate molar ratio, you actually decrease your solubility of the solution. So urea is actually seeming to inhibit the solubility of hydroxylapatite within this system. But urea actually seems to be somewhat necessary within this system in order to drive down the water, because as I said, apatite is insoluble in water, so if we have any water in the system, we need to drive enough of it off in order to solubilize this phosphorus mineral. So there's a point at which about 75% water, if you have more than that available, you no longer have the solubility of this hydroxylapatite. But again, when you're talking about the fact that is this system robust, we can see that there's still quite a range here in which of molar ratios that you're going to have this system available that will solubilize your hydroxylapatite minerals. So just a quick conclusion to go over it. The solubility of phosphate minerals is actually controlled by the molar ratios of this UAFW system. Dissolution of phosphate requires a liquid medium, but at the same time, we don't want too much of the water available. And as long as the UAFW remains in this liquid system, the solubility of the phosphate mineral will be enhanced, and greater enhancement comes with a higher amount of ammonium formate versus the urea. We're hypothesizing that urea's role within this system is actually as a condensing agent, that it doesn't do anything for the solubilizing of the phosphate or freeing of the phosphate, but that it is actually helping to drive off the water within the system and make a eutectic, and that the ammonium formate is actually the chelating agent that is taking the phosphate out of the calcium phosphate mineral. And with that, I would like to acknowledge my collaboration within the CCE, my lab mates at USF for all their help and encouragement, and of course our funding gods, NSF and NASA.
Thank you, Jennifer. We have time for questions. Dave, you're first up.
Yeah, hi, Jennifer.
Hi, Dave.
In an open system with ammonium formate,
Yes.
the ammonia, NH3, will leave the system.
Right.
It'll become more acid because leaving behind formic acid. Therefore, acid alone can solubilize the apatite.
Absolutely. And I would like to and have not done yet to determine the final pHs, but as you could see in that picture, because we're using just a small amount of the UAFW solution, it's very difficult to get an actual pH on those amounts at the end. I'd like to try a larger based experiment so that we can determine the pH as we go along.
Try putting in a pH-sensitive dye. It should give a color change.
Okay.
And feel what might form.
Perfect. Thank you. I'll do that. Thank you.
If there are no more questions, I'd like to thank Jennifer Lago,